Welcome back to Computer History with Chris Garcia. I am, in fact, Chris Garcia. Today we're taking a sidestep, something I didn't expect to do, but now I'm going to. And it's about the early days of artificial intelligence. And this is an area that's near and dear to my heart. It's one of the areas I sort of half focused on while I was at the Computer History Museum. Because a lot of stuff gets folded into it. Computer graphics, music, and art is often sort of lumped with AI. And that's largely because of places like SAIL, the Stanford Artificial Intelligence Lab, and the sort of the breadth they had in the early days. But when you started, actually, again, it all comes out of World War II. And oddly enough, it was something that happened during the war, when Warren McCullough, who was a neurophysiologist, and Walter Pitts, who was just 19, and they proposed a model for how neurons actually perform logic operations. And the idea is really basically simple. A neuron either fires or it doesn't. That's a 1 or a 0. Now, we kind of do know that this isn't necessarily entirely true. We think neuron computation is actually done in more of a quad or quinary or quadrary form. So it's either a 1, a 0.5, a 0, or it's a 1, a 0.33, a 0.66, or a 0. There are lots of possibilities there, but we know it's not as simple as 1 and 0. But at this point, they didn't. But what's interesting is that formalized thought as computation. And that's really, really key to this whole thing. Now, it wasn't until after the war that Norbert Wiener wrote a book called Cybernetics, or Controlling Communication in the Animal and the Machine. And this is an idea of how computation and thought sort of come together in a series of systems. It is a look at thought as a biological and mechanical process. And of course, there are things like feedback, communication, regulation, all of these sort of ideas that you can definitely put between the two of them. And one of the core concepts is that machines act to reduce error. That's one of the things. And they're always trying to speed the path between the goal and the output. It's a really interesting sort of idea. And when you look at the early sort of feedback systems, and particularly today, you can see Wiener's sort of ideas sort of permeating through to a degree. And these were before the large-scale presentation of computers. You had electronic and electromechanical computers already. But we didn't have the speed to be able to do a lot of really interesting things. Now, what really gets fascinating is in 1950 you have Alan Turing. And arguably the best known concept in artificial intelligence first 50 years. And that, of course, is the imitation game. Now, the idea of the imitation game, or now it's called the Turing test, is pretty simple. You get 2 or more inputs through a screen. And the end user needs to figure out which is human and which is a machine. And this does have some issues with things like how much do people's desires to be talking to a machine enter into this? Or how much do their desires for them to be wanting to talk to a person enter into this? You could also get way postmodern into Derrida and all of that about mediation of all form through language. It gets deep. But Turing wasn't necessarily thinking in terms of an artificial intelligence. He was thinking in form of calculated, influenced release. I guess that's the best way to sort of put it. He thought machines could learn, but it also wasn't quite that cut and dry. And someday someone will do a really good podcast on the entirety of Alan Turing, because he was a really smart guy. Hey, speaking of smart guys, this is the first guy on this list I've actually met. And that's Claude Shannon. Claude Shannon was a polymath. He was a big thinker in many ways. He was also a very funny guy. And one of the things he did that really influenced ideas that exist within computation is called Theseus, which is also called the mouse maze. And what he did is, using magnetic logic, he developed a mouse called Theseus that would navigate through a maze. And it would learn the shortest path. So it would make an error and it would hold it in memory and it would move on and so forth. Very, very, very simplistic on one level. And it still exists today, apparently, in the MIT collection. Didn't know that. Very excited, because now I might be able to see it someday. But there's video of it. Because you would go, sort of how it worked is, you would go through the maze, and every successful move flipped a relay. And every failed move didn't. So you knew that when you got to a specific point, oh, this relay needs to be flopped, that goes this direction. It's really an interesting concept that was made very simple. And this is something that Shannon was good at. He was great at taking the big idea and winnowing it down to a demonstration that makes sense. Remember, the history of computation is the history of being able to make people realize what's actually happening. This also is what gave us video games, but we'll go there later. Well, we already kind of did. Now, Dean Edmonds and the second person on this list I met, Marvin Minsky, actually had a really interesting thing. And something I know very, very little about, sadly. But when I started looking into this, I really discovered that this is a really interesting point. This is called snark. And so the idea is this. They wanted to develop a very simple brain to reason out a maze. Same thing as Shannon's, but they wanted to do it on a different model. Instead of a more simplistic, relay flipping model, they wanted to do a reasoned model. And so they used 300 vacuum tubes to make 40 neurons. And the idea was, of course, to simulate a rat in a maze. And this is one of the first applications of actual cybernetic concepts. And they made it, of course, like a lot of stuff in the academia at the time, from salvaged military surplus. But this is really interesting, is that they were working on reinforcement ideas, learning, machine learning. And it's utterly simplistic by any of today's standards. But it is definitely an application of electronic computation towards artificial intelligence. Now, the US wasn't the only group doing this. In Europe, and in particular the UK, 50, 52, 53, you had several people sort of popping up. One, you had Turing there. You had Dietrich Prinz, who wrote a chess program for the Ferranti Mark I, but it was only capable of doing mate and two problems. And the history of computer chess is gigantic. I know. I'll do something on it someday, but we're not going to get into that all the way here. Christopher Strachey, I talked to his daughter once, I think, which could actually play full chess, or full checkers. Now, what's interesting is that all of this is being done on very early computers. The Ferranti Mark I is sort of the machine at that point. But what's interesting is that they're using processes that are somewhat reasoning, but they're within bounds. There are a finite number of possibilities in checkers. There really are. For example, you have, I think it's only 16 opening moves in chess. And checkers are only 4 opening moves. No, 6 opening moves. 1, 2, 3, 4, 5, 6. I think. It's confusing. So checkers is infinitely, but it's still bound, even chess, in the mate and two. And being able to demonstrate that, algorithms and so forth can be used to reason out a limited space concept definitely informs later work. And we were seeing things like early machine translation. The IBM 701 was used to do that in 1954. And this is, of course, natural language has been a goal of, and automatic language translation has been a goal of artificial intelligence pretty much since the beginning. And this actually received a lot of press, and one of the reasons for that was that it was IBM. And that is major turning point in all of this. Once IBM was shown to be getting into a point that would traditionally have been deep academia and getting press for it, it is starting to expand the idea of the entire space that is artificial intelligence as we know it today. But it wasn't really until 1956 that the most important single moment happened. And that is the Dartmouth Summer Research Project on Artificial Intelligence. And the original proposal of that came from the third person on this list that I knew personally, and the one who I knew best actually in this episode, is John McCarthy. And the organizers were Shannon, McCarthy, Minsky, and a guy I've only heard of a few times, Nathaniel Rochester. I don't know hardly anything about him. But the proposal could be sort of winnowed down to this. Every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. Think of that. It's saying that a machine is flexible enough in concept to do any of this. But we just don't understand the processes we are trying to imitate enough to do it. That becomes a major point in the entirety of artificial intelligence research. And there were some really huge names here who had gone. Oliver Selfridge is one. Arthur Samuel, Alan Newell, and Herb Simon. I also heard once that the developers of BASIC were there. It would have been fairly early for that. Kurtz and Kemeny. Kemeny might have been, but I think Kurtz would have been too young. But there were all sorts of work done in here that looked into various areas. Machine translation, of course, was one. Object recognition, natural language, things like how coding can be made to simulate thought processes. All of this stuff was happening at this point. And coming out of that, we have a whole bunch of really cool stuff. We have Selfridge's perception model, Pandemonium. And this is done at the National Physical Laboratory, NPL. And it was sort of a framework for pattern recognition. And it gives the idea of sort of what entirety of neural networks have been based on for the majority of the time, of the neurotree, where tree making and pruning and all that happens. Really interesting concept. At the same time, there is perceptron at Cornell, done by Frank Rosenblatt, which sort of was, again, recognition stuff of, you have very simple sort of 8x8 grid, and you can recognize what is being shown there using the computer. It's interesting because this got a lot of press, of course. But the real thing here is that it is, again, a narrow set. And they're applying computers to a narrow set of something that is traditionally thought of, or at least was, as a human-only aspect. Now, McCarthy wasn't just an administrator, though he was apparently pretty good at that. He wanted to come up with a system, a program with common sense. And he didn't want a sort of a mechanical brain. He wanted to show that the brain was a machine in much the same way that Turing did, but a far more robust concept of it. And he came up with an advice taker, which was a program that could modify its behavior by absorbing new logical statements. And this isn't an expert system quite yet, but it is certainly laying the foundation for that. And if you look at programs that are more recent, like dear friend David Cope's wonderful program, Emily Howell, this is the entire basis for that. This idea of being able to send feedback and the limited nature of that, in this case, very simple logic sort of program, makes it really impressive. Now, at this point, we're starting to see a proliferation of AI concepts. Lots of people are doing computer chess. Lots of people are figuring out ways to do route planning in particular is one that was people always wanted to figure out. How do we do fast route stuff? The traveling salesman problem, for example. And we start to see labs founded. And the first of them, the first important one, is the MIT AI Project and Project Mac. And that's at, of course, where better than the Massachusetts Institute of Technology, MIT. I went to Emerson College, which is the next best college to MIT. Well, it's a college that was next to MIT. But you had Minsky and you had McCarthy. And this is 1959. And they start doing some interesting stuff there. They're doing things like theorem proving, working on symbolic logic, and of course, vision systems. Because the funding came from the Office of Naval Research, and a little later on, from ARPA. The work they were doing, and the government saw that there was 100% possibilities in the application of artificial intelligence concepts to their work. And that makes sense. You can explain to, I guess in general, that they need funding for a project that can identify, for example, theoretically, identify potential nuclear weapon sites. That's a big deal. And once Project Mac and the AI project at MIT was founded, everyone got involved. They bought, I believe, an IBM 7094 was the big computer there, I think. I'm not 100% sure on that one. But the folks who were there, Seymour Papert, we'll talk more about him later. Joseph Weizenbaum, a major figure who we'll also talk about a little later, but much closer. Like, all of these people were there. And this was the first major AI center. Now, once we get into the early 60s, we're seeing places like RAND, like Bell Labs, and of course the labs that have already been founded at Stanford, CMU, SRI, in the UK, NPL. There was a information processing language, which is called IPL, which was formed and written by Alan Newell, Cliff Shaw, who I think we mentioned in the episode that we talked about Johnniac, and of course, Herb Simon. Oddly enough, I think the only one of them I met was Simon. I'm not 100% sure on that, though. But it's a list processing language that's used to do sort of general problem solving. And it was interesting, but it was clear that you needed a lot more stuff to make it really useful. You also had a thing called Saint, which was out of MIT, which was a project that solved symbolic integration problems in freshman calculus, which is interesting because it's solving integrals. And it's higher level. So again, it has a limited scope, but it's again broader than what they were doing before. Just like in the general of computing, where you have your three big things: smaller, cheaper, more accessible. Here, you're getting more widely applied. It's an interesting sort of inversion. I like to say that AI really came to fruition in 1962. That's because John McCarthy left MIT and joined Stanford to found the Stanford AI Labs, SAIL. And once that was founded, with money coming from IPTO, the Information Processing Techniques Office, J.C.R. Licklider, the big figure there, and he's a huge name who I really don't talk about much, but I really should. And the ARPA money that was coming out of that was great. But they were doing so much. They were doing theorem proving. They were doing time sharing systems. They were coming up with logic systems. But most importantly, to my view, they were doing robotics. And once you have robotics entered in, you've opened up a huge door. Because robotics predates artificial intelligence. So it's sort of been rolled in. What's interesting here is at about the same time, you have Larry Roberts doing a thing called computer vision, which is trying to do object recognition and edge detection, which is actually pretty complicated. And definitely influenced the folks at Stanford Research Institute, SRI, because they did something huge called Shaky. And Shaky was an autonomous robot that would take all of its sensors and get all these readings, and then it would send it off to a mainframe that would calculate it and send it back and then move a little and back and forth and back and forth and back and forth. Could go like 2 meters an hour. Not exactly blazing, but a huge step forward in the ability of a machine to operate without human intervention, to logic its way through a room. You have stuff here that's going on. You have Dennis Mitchie, who did a thing called the Matchbox Learning, or Menace, which is really just, it's an optimizer, is the best way to put it. So you'd have all of the possible moves in tic-tac-toe. And this is literally a low-tech demonstration. That's all it is. But it is a way of understanding how pruning works, how sort of learning reinforcement concepts go. And it's sort of a sidelight, but it is interesting in that you can still see how this stuff goes out. And Donald Mitchie went on to have some very impressive credentials. Now, in 1965, you get what I consider to be the most important early step after Lisp. But we'll get to Lisp later because that's a bigger picture thing. I'm probably going to do a whole episode on Fortran, COBOL, ALGOL, Lisp, and BASIC. So I'm going to do a whole episode on leading up to BASIC, probably next. Now, what's interesting is Dendril was the first expert system. And one of the guys who built it, Ed Feigenbaum, still around today. Really the last of the first generation still around. Don Knuth is around too, but he wasn't as much hands-on in the AI side as he was in the bigger picture computational type stuff. But Feigenbaum, good guy, known him fairly well over the years. Had wonderful lunches with him a couple times. But the idea here is using Dendril to infer molecular structure from mass spectrometer data. That's insanely important. And again, it's constrained, but it's broader than previous constraints. And it's the idea of applied expertise that changes everything. This is where we are today. Honestly, what we get from ChatGPT and all of that, Dendril is what made that possible because of this general mind shift. From being an everything, making a brain, to modeling a function of the brain. Hey, if we're going to talk about ChatGPT, let's talk about ELIZA. And ELIZA was I've heard it called a pattern matching algorithm, but I don't believe that. It is meant to be a model for interaction between a therapist and a psychotherapist and a human. And what's interesting is that it's very simplistic. It just basically asks you a question every time. How long have you felt blank? Do you ever blank? When was the last time you blanked? That sort of thing. It's not quite random because it is being given the code, the clue, from the person who is interacting with it. But what's amazing is, and this is something that I don't know if it existed at all in artificial intelligence before this point, where the individual began opening up more and more and more with the machine when it interacted with ELIZA. And there is the thing called the ELIZA effect, which is where you project meaning onto superficial behavior. In other words, you act to a machine that is just doing what it's programmed to do, as if it's a person. In very limited ways, ELIZA probably could have passed a Turing test. It's simplistic when you use it today. There was also a follow-on called Perry. I don't remember if it was someone else who wrote it, that was used to train psychologists and psychoanalysts and all that for dealing with paranoids. It's an interesting sort of world there. Now, with all of this, we now have the beginnings of several different parallel revolutions. AI as a informations systems concept. Because one of the things that a lot of people wanted, and you started to see expert systems being built for, was logic optimization. That dates back all the way to McCarthy in the early days at MIT, and even before that. This idea that we can use our systems to design our systems. Now, one of the fascinating things about this whole operation, though, is that when you look at the other areas, because, we want to have logic optimization, we want to have pattern recognition. Because pattern recognition has massive real-world applications. In particular, pattern matching would allow you to, again, notice a, Russian site where a bomb is. Or even better, it allows you to identify people's faces. And I want to say they started doing that sort of thing about 1963 or 4. But again, the ways they could do that because of the limitation of the technology was very limited. That has gone on through to today. But you also had this other side, which is an interaction side. And this is the side that has become the most ingrained in us today because of things like ChatGPT. And the idea has always been to get more and more human as things progress. This has changed now if you look at the path of ChatGPT, it is actually now designed to be less human because people were misusing the humanity level, but we'll get to that in 10 or so years. But the early history of computers and the attempts to model human thought processes, majorly important. And once things like Dendril and expert systems that help to design circuit design, you saw the application really becoming vital to the mainstream of computation. And we'll talk more about this as we go. Every, probably 10 years, we'll probably do another one of these where we'll look at what these mean and how artificial intelligence has bloomed at that point. Yes, I will do one on computer graphics, music, and art. It's coming up, I swear. But that one's going to be 3 times as long as this one. But another thing we are definitely going to talk about is BASIC and Dartmouth time-sharing system, because now that BASIC is an orphan with the passing of Kurtz and Kemeny many years ago, I'm really interested in looking at that sort of idea as a sort of a standalone. But yeah, there's a lot more stuff to come before we get to the IBM 360 series, which is really the tentpole of the 1960s. But I want to do more other stuff too because it's more fun to research. All right, thank you for listening to Computer History with Chris Garcia. I am in fact Chris Garcia, and I will, indeed, see you later.